Okay, welcome back, everyone. We're very happy now to have our own Victor Rodriguez, who will tell us about bootstrapping the Ising model on the Lattice.
Okay, so let me begin by thanking the organizers for the opportunity to speak and also for putting together this wonderful workshop. Whoops.
It's a sign for chalk.
Yeah, so on that, so as a relatively newcomer to this world of optimization, I've had an incredible fun listening to the rest of the talks, and yeah, so thank you to the organizers. So today I'll talk to you about if you want the K-side problem, but for physicists, so something very basic that it's not a problem. This is actually a model, so that people in physics like to study and that we learn a lot from. And today I'll tell you about how to use ideas of optimization in this particular model. So this is based on this work in green here with the collaborators listed here, but also pictured here. Min-Jae Cho, who's one of the organizers of this workshop, Baraga Bai, Yingsun Lin, Joshua Center, and Shi Yin. So if you have further questions after the talk, and you want to discuss things further, please feel free to find any of us, and we'll be happy to do so. Okay, so let's begin. Here's a brief outline of today. So I'll give a brief review of what the Ising model is and why it's important and why we really like to talk about it. And then we'll jump into how to quote-unquote bootstrap this model with the two main ingredients that we've already heard of in some ways in this workshop. The first ingredient is a relation between the variables we wish to study, and the second ingredient is, of course, positivity. And we'll try to combine these using optimization, and right after that I'll present some results for the observables that we want to study. Okay, and then I'll finish with some prospects. Okay, so let's jump into what the Ising model is. So the Ising model, so you start with a lattice, as in here. I hope it's not too hard to see, but the lattice points are in gray. So at every lattice point, lattice side x in this lattice lambda, there's a variable that we call the spin, s of x, which is very simple. It only takes two values, plus or minus 1. And colloquially, we just call it spin up and spin down. The reason is that the Ising model, as we'll see in a second, a good intuition to think about this is that of a magnet or a magnetizable material, which is made up of many tiny magnets, each of one of these lattice points. And each lattice point can spin up or down. So it's like a tiny magnet or a tiny electron at each side. Okay, and given spin configuration of the lattice system is a particular assignment of plus or minus 1 for each of the lattice sides. So for example, here's one particular spin configuration, some ups and some downs. Here's another example, some other assignment. And the statistical sum that we want to study is in here. So we perform infinite sum over all possible spin configurations, for example, this one, weighted by this measure, this exponential factor. Here's a factor of the temperature, and weighted by the energy of such a spin configuration. Okay? Which is interpreted as the probability that the system is in that particular spin configuration. Okay, so let me tell you what the Ising model is. It's one of the simplest choices for what this energy of the spin configuration is, and it's here. J and H are two real numbers, but let me tell you how to think about these two terms. So let's start with this one, the second one. So the way to think about it is it's supposed to model the effect of an external magnetic field, which I pictured here in this yellow arrows, say pointing in the opposite direction. And so the intuition is that spins it's energetically favorable for each tiny spin to point in the same direction as the external magnetic field. So the energy gets lower if it's pointing in the same direction, so that's why it's energetically favorable. Okay, so that's why we have this term, and to get the total magnetic field, you just sum over all the tiny magnets in the lattice. The second term the first term here, it's supposed to model the interaction between the tiny spins themselves. And the intuition again is that if we have, for example, one spin side pointing in the up direction here in red, its nearest neighbors. So the Ising model, the very special thing about the Ising model is it only has nearest neighbors interactions. So this is what I mean by this bracket. It means that it only talks. So if X is the red one, Y is the black one. It only talks to those that are directly adjacent to it. And the intuition again is that if the red one is pointing up, then its neighbors really do want to point in the same direction. It's energetically favorable to do so. Okay, so J is just a parameter of how strong is the strength of interaction between them. So we call it ferromagnetic if J is positive in this situation that they want to point in the same direction. And if it's negative, it's called antiferromagnetic, so in which it's energetically favorable to actually point in the opposite direction. Today I'll focus on the positive one, ferromagnetic, for good reasons, as we'll come back to later in the talk. Okay, so that's it. This is a very explicit Ising model. Let me just summarize it here. The partition sum is you sum over all spin configurations, all possible values of plus or minus 1 for every spin side, weighted with this distribution here. Okay, and if you want to compute some observable, so colloquially we call it the average value of some functions of the spins. You stick it into the sum over all spin configurations, and up to some normalization of this factor. And again, this is supposed to be the probability that the system is in the given spin configuration. Okay, so that's the definition of the model. Let me just point out that there was a factor of the temperature, but I just absorbed it into these constants. These are real constants, just to make it simpler. Okay, so why is this important? So it's because one of the simplest models that exhibits something called a phase transition. So let me give you the intuition of why this happens. So let me plot what's the expectation as we increase J, and J again is the strength of the coupling between the spin sides. So let's imagine that J is very tiny and the positive, right? So that means that they don't really, the coupling between them is very weak. So we can, for the most part, forget that they're actually talking to each other. So they want to align in some random way. So mostly plus or minus, but really no correlation between them because they talk to each other very, very weakly in this extreme. Okay. Let's go to the other extreme. What if the coupling J is very strong, so they really want to be talking to each other? And the idea is that they'll be pointing in the same direction, say up in the up direction in this picture. So most of them, if they talk to it very strongly, they'll want to point up in the same direction like this. And this is called spontaneous magnetization because suddenly as you start increasing the strength of the coupling between the spins, suddenly this behavior, they're going from kind of some random assignment to really pointing in some particular direction. And so somewhere in between, there's a transition from this sort of behavior to this behavior, and we call it the critical coupling, the critical strength between the spin interaction. Okay, so one diagnosis of what this transition is, for example, the average value of the spin at any given site. So I called it a 0 here. And what we saw, just in this intuitive picture, is that somewhere here when the strength of the coupling is small, it's expected to be 0, whereas here in the other extreme, when they tend to point in the same direction because they are very correlated, it's supposed to be non-zero. So that's one diagnosis to see that the phase transition is occurring as a function of the coupling. And we'll come back to this. Okay, but hopefully the intuition of magnets is clear. Okay, so then the phase diagram, what I described in the previous slides was I turned off the magnetic field, so we were just looking at this axis here with a critical coupling here. And this is the picture more broadly as we vary these two constants in the Ising model, the strength of interaction and the magnetic field, the external magnetic field that they're placed under. Okay, so then this is the critical point. Let me just mention here that this special point here, and only here, is the subject of a conformal bootstrap, as we saw in the previous talks by David Pollan, Bob and Reese. And so the conformal bootstrap focuses on only this point, for very good reasons, of course, because these are the points that exhibit universality and go beyond the description of the Ising model. But today, we won't do that. We will try to analyze this particular model that has any place in this parameter space of the external magnetic field and the coupling. Okay, but just to contrast. Okay, so this is called the second order phase transition point. And this line is called the first order phase transition line here. Okay, so that's the picture that we wish to study. So let me summarize what is known and what is not known about the Ising model analytically, explicitly. So in 1D, so just one line of spin sites, the model is actually exactly soluble, so you can write down any observable you write down an explicit formula for spin correlators. And it turns out that in that case, there's no phase transition, so perhaps it's not as interesting. In 2D, famously, it was solved by Onsager, but only for the zero magnetic field case. And it does exhibit a phase transition. So for example, I plotted it here as a function of the coupling. The spin magnetization, this spin average value, has some nice formula. Not important what the precise shape is, but there's a nice formula like this. Signaling the phase transition of having zero magnetization to suddenly something non-zero magnetization. But for so such nice formulas are not known even just as soon as you turn on non-zero magnetic field. And this is sort of the place that we want to make some progress on. And in 3D, nothing is known analytically. So here, yeah, questions?
I think I missed something. So
yeah.
The assignment that you get is the one that minimizes that energy? Or?
Yeah. So that's the preferred one. But you're supposed to do sum over all possible ones.
Sum over
all possible.
Then for any J, no matter how small, you want to align everything, right? How can you beat that?
Right. So the thing that happens, this is very non-trivial, but the thing that happens is that when this coupling between them is very small, there's no correlation, so it's actually just 50-50. So it's basically 50% of the spin configuration is going to be pointing up, roughly, and the other one down. They cancel each other, and then you just get the average value to be 0.
So maybe just to clarify, I think Ahmed is asking what is the question we are after? What does solving mean? And it means, I think, computing Z, right?
Yeah, for example. Or computing this kind of average values of different spin configurations. So for example, computing this curve would be one goal. So for instance, computing this curve was done by Onsager,
so it's not like finding configuration. I mean, it's not like
no.
It's just integration.
Okay, so magnitude would be the minimum of the distribution. In here, it's sort of the minimum of the support of the distribution. In here, you're interested in the whole distributions.
It's because there's a combination between energy and entropy. So it's not just about minimization.
Okay.
Sorry, what
yeah.
Can one produce, I mean, even in the 3D case or in the 2D case with the field that one cannot solve it exactly, are there good numerical ways of
of course, yeah. So there's Monte Carlo simulations of this. And of course, that's, for instance, one way that we know, apart from rigorous mathematical results that establish that there's phase transition, in practice, people have simulated this by Monte Carlo, and they also see that there's some phase transition behavior like this one. But today we want to follow a different approach, the optimization approach, complementary to this numerical one, so Monte Carlo one, with the hope that this will lead to some rigorous results on such kind of observables.
So what is the meaning of the y-axis?
This is the. So I haven't defined what this curly brackets mean. Sorry for that. I'll count that into 1 or 2 slides. But this is the average value of a single spin site, its value. For that, to compute this, you need to sum over all possible spin configurations. I'll give you the precise formula in a second.
Okay.
Okay?
In writing that formula, did you set JC to 1? It's a little hard to read.
No, this is a function of J. So you're not supposed to look at it too much. It's just that that's why it's a grade. So it's just that there's a very explicit formula. that is solved by one side.
It has to vanish at j equal to jc. Right?
Oh, right. Yeah, I set it to 1 in this one. Yeah, thanks. I think. Yeah.
The power is 1/8, right?
Yeah, that's right. Okay. Thanks for that. You have very good vision. Okay, so today we'll follow, the bootstrap philosophy. So it's like, okay, maybe we don't have a nice analytic formula for what this looks like in general, but still, if we can put some bound on our ignorance, so that's the philosophy, that's still useful, especially if it's rigorous. And even better, if we can have a systematic way of improving these bounds like this, that would be the hope. In order a different approach to solve this kind of model. Okay. So with this, let me begin by describing how we do this in practice. Okay. So so here's the formula that I promised. What are, and more precisely, the spin correlators, which are the observables or the objects that we wish to bootstrap. So what it means is you choose a configuration of spins, a product of them, like this, for example, with the most generic case. Stick it into the partition sum, weight them with this probability distribution, sum over all possible spin configurations, normalized in some way, and that's what we call the average value of such a spin, number of spin insertions like this. Okay, so some examples are, for example, this one, or for example, this one. We'll be studying the average value of the product of the 2 adjacent spins. Or for example, this one, the two spins that are separated by 1 empty one. But of course, it could be any generic configuration that you wish to compute. So this would be the variables that we want to solve for or put bounds on. And then, for example, an important one was the single spin one that I showed you, that is the diagnosis of the phase transition. Okay, so those are the objects. Okay, so these are just like moments in some distribution.
I'm sorry.
Yeah.
Can I ask you?
Yeah.
I've been bothered by this actually previously, but anyway, I'm going to ask. How do you take this infinite in the energy? How do you take this infinite sum of Sx? What does that mean? Because do you sum over the whole lattice plus minus? What is the meaning of that?
Yeah. So you have to, one way to define it is to start with the finite lattice, which is a very explicit sum, and you have to take the infinite size limit in a careful way.
I see.
Yeah.
Okay.
And of course, this is something that mathematicians do very carefully, and we know how to do. Okay, so we won't obviously won't do that explicit sum, right? This is an infinite lattice. We'll try to bootstrap it.
Well, we do need to use that to prove positivity.
That's right. So
That's
some
not
of
very hard
the
to-
positivity relations that we'll use depend crucially on being an infinite lattice. So we don't want to be in the infinite lattice. Also, the infinite lattice is the one that exhibits this phase transition. So that's why it's also important to be in the infinite lattice. Okay?
So for how big an n can you do like just full sum without Monte Carlo? I mean, it's to the n terms, right?
Yeah. So I mean, the strict infinite sense, you cannot, right? And the point is that we won't need to do that explicit sum with this approach.
You can do like 4 by 4.
Yeah, of course.
But if you just sum, you don't have to bootstrap. You just do the sum.
Right.
Yeah.
I mean, you can't go very far.
Yeah, in 3D, it becomes untractable pretty quickly. Yeah. Okay, so these are the things that we wish to solve for, to bootstrap. So the first ingredient for this approach is a relation between these variables, a relation between these different spin configurations. So where does it come from? So it sounds pretty simple. We get a bunch of relations just by doing this change of variables. Just flip the sign of one of the spin sites in blue here. Okay. So let's consider what that does. Sounds kind of trivial, but we'll see that it'll lead to something interesting. So the very special thing about the Ising model is that it only had interaction terms between directly adjacent spins. So the only things that get affected are these flat dots if we're flipping just the blue one. So more specifically, these are the terms in the in the Hamiltonian of the Ising model, the exponential measure, change sign. So SZ flips a sign, and then its nearest neighbors in all positive directions. And also, of course, the magnetic field term, just like that, a flip sign. So let me add and subtract this, the same thing, just so that I have the original measure with the plus sign. Okay, just some rewriting. And so then, in that way, we can see that now, we can put back the infinite sum. So we get a relation between different correlators. So in this, on the left-hand side, is just a spin correlator we started with. And the right-hand side is what we get after we do this flip of the spin. Okay, this theta is just some sign, just saying that you flip the sign as well if this SA contained this blue guy that we flip sign. So it's an extra sign there. But the important point is that we get this exponential factor. Now, one more thing is that recall that all of these variables, S of x, are very simple. Just take the plus or minus 1 values. So, of course, we can expand this exponential to get something finite, some finite number of terms. Okay, so I just call this combination W, and because it's made out of this S's, it has some finite. If you expand the exponential, you get some finitely many terms. Okay, so it looked nasty. It's some exponential, but if you expand it, then it's some finitely many terms. So very concrete. So let me give you an example. So just to make it a bit more tangible. Oh no, before the example. Yes, so this is how the relation looks. It's a bit ugly, but it's very nice. So let me just point out that it's linear in the observables we wish to constrain, like this, with some coefficients that are depend on the constants of magnetic field, and these A's and B's are some functions of J's, some cinches and coches of J's. Some very explicit. But the important point is that they're linear, and as we'll see in a second, they're equations between variables within a small region, because when you flip the sign, only things that are around it are affected, but nothing else. Okay, so let me give an example to make it more tangible. So we'll consider this small region. We call it 1, 3, 1 diamond. So we only got this 1 and then 3 sides and then 1 side. And we'll consider what happens when we flip the center guy. Okay, but before doing that, let me just say what the variables are. They're just within this region. So they're these ones. So for example, we can have 2 adjacent spins here, or the one separated by 1 empty side, or this diagonal one, or these 2 guys with 4 spin insertions. Okay, and within this diamond, that's all there is. For simplicity, I'm assuming that the ones with an odd number of spin sides are just 0. I'm assuming that I'm in the phase that those are 0, just to show it in just one slide. Okay, so these are only 5 variables within this small region. Okay. Now, what happens if we flip the sign of the center guy? We'll get some linear relation between these variables, as we saw. So again, this is a bit ugly, but just to make the point that it's something very explicit and finite, and a relation between these 5 variables. Okay, just by doing the seemingly trivial thing of just flipping a sign of one of these, the change of variables. Okay, and again, Igor, you're not supposed to look at this, but it's just that they're very explicit, so depend on J and so on. Okay, so some linear relations, and then we get many. The point is that you can flip the sign in the correlation function of each one of these guys. Flip the sign of the center guy in this correlator, and this correlator, and this correlator. You get a bunch of these linear equations. Of course, that seems like too many. For example, in this case, we get, in fact, as we just counted, 6 such, we call it spin flip equations for these variables. But of course, they're not all independent. Some of them are highly redundant. And in fact, out of the 6, only 2 of them turn out to be independent. And we can use them, for example, to solve for 2 of these variables, say these 2 guys, for example, in a linear fashion like this. Again, don't pay too much close attention to the actual form. It's just to show you, convince you that it's something very explicit. X4 and X5 are completely determined, and once you know X1, X2, and X3. Okay, so again, emphasize the main points. They're linear relations, and they're equations between variables in a small domain. This is the example that we just discussed. But of course, you can go to slightly larger regions. So for example, you can consider in this 13531 diamond, like this, what happens, you get a bunch of equations by considering flipping the sign of all these blue guys in this skeleton. And because the Ising model is simple, it's only interactions between nearest neighbors, it only affects one more side, so these black ones here. You can do the same, I showed you the 2D version, but you can also do it in 3D. You consider what happens if you flip the signs of these guys, you get a bunch of relations between variables and only this domain, so this small domain. Okay, so that's the main point. So that was the first step, a relation between the variables we wish to study. Okay, and just to give you an idea of how big this problem is, just in hopes that, well, not here yet, but hopes that experts in the optimization community can give some words of advice on how to tackle these problems. Maybe not on this side, because this turns out not to be the bottleneck of the computation. But of course, we did this first column in the smallest 131 diamond, where we saw that there's 6 naively variables. Here I'm including the empty set, so it was actually 5. But some spin-flip equations, and then once we solved those linear equations, it turned out that only 3 out of the 5 variables were independent. And of course, it gets kind of big once you start increasing the region in which you start flipping signs. So for example, in the next one, there was like 500-ish naive variables. But after considering all the spin-flip equations, of which there are many, and many also independent ones, they get reduced to only 19 independent variables. Okay, and in 3D, of course, the numbers are a little bigger. So 5,000-ish get reduced to 600-ish variables, just to get an idea of how big the problems are becoming.
So,
yeah.
So the high-level idea is to somehow reduce the number of variables and then do some computation to estimate these quantities. Is that where we're going?
Yeah, well, I'll impose some positivity conditions, which in combination with this exact relations, I'll phrase it an SDP problem and then put bounds on these variables. Yeah, I'll write the SDP problem in well, some time after these slides. But the first step is just to realize that there's a lot of redundancy in the description. So and then we're trying to harness that redundancy. And you see, it's kind of extreme. It's just like very comparatively small number of independent correlators. Okay, so of course we do this numerically because there's many variables. But if you do it in a smart way, then it's not really a problem. At least up to this size problems that we've considered. Okay, so that's the first step. Now we'll come to the positivity aspect of this work. And in this, there are several kinds. Some more obvious than other ones. There's one that will be they'll talk about, which is reflection positivity. The other one is a square positivity, which has appeared in other talks in this workshop. This is the more obvious one. Just square something real, and you get something positive. That appears to be redundant in the sense that bounds that we obtain if we impose this, do not improve the bounds that we obtain from reflection positivity, for example. So I mostly won't talk about this one. I'll talk about the maybe not so trivial ones. And there's other types of positivity conditions, a lot more sophisticated, that mathematicians have studied over the years, which I'll briefly describe as well. Okay, so let's start with the first one, reflection positivity. So this one just says that if we take any real linear combination of some spin insertions, it is some arbitrary linear combination, but only half the space, half defined across a plane. I'll come back to what these planes are, but it's just on half of the plane. And then you multiply it times the same linear combination, but with the reflected mirror image across that plane. Like, for example, in this, the blue ones. Okay, you multiply them together, and then evaluate the infinite spin sum. You evaluate the average value. That is supposed to be positive. So that's what reflection positivity is. Okay, it's not so hard to convince yourself that the independent reflection planes that one can consider are these ones. This one that cuts across the spin sides like this, vertically, and the other one that goes in the middle of the spin sides, and one that is diagonal like this. Okay? Let me just point out, for example, that this guy in the middle that cuts across the links, the proof of such a statement requires that the coupling between the spins is positive. So that's why I've been focusing on the so-called ferromagnetic one, in which they want to spin in the same direction. They want to align in the same direction. There's one technical reason why, because we want to impose more positivity, so then we focus on that case. But so we have all these three types of reflection positivity.
So it's only with respect to these kind of. What happens if you take some sort of weird irrational sloped line and you cut the plane?
Oh yeah. So we want to preserve to be able to relate to use it on the same spin correlators. We wanted to preserve the lattice. So for example, take this one and cut it like somewhere in between. It's not going to preserve the lattice.
Okay.
Okay. So these are the three dependent reflection planes. And I won't have time, even though the proof of this positivity is a little bit instructive. I won't have time to describe it in detail, but so this is what it looks like. It's similar to the square positivity. Okay, that phrase says the positive semi-definites of a matrix. So we can phrase it like this, where the positive semi-definite matrix of this correlation matrix, where you multiply the given spin configuration here times its reflection across the given plane, evaluate the expectation value, the average value, and that is supposed to be positive semi-definite. All right, so this is how we're going to impose it as an SDP problem.
So this works for linear automorphism of the lattice, or somehow is it special about this lines? Somehow any like.
Let's see. It's important that it has to be the same configuration across the mirror plane for it to be positive.
Any involution or.
Yeah. Mm-hmm.
Involution is important. Yeah.
Okay. Okay, so let me go through an example how we actually use this, just so that we're on the same page. So let's go back to the simplest case of the 1-3-1 diamond, and we'll consider reflection across this vertical plane. Okay, so where we had these 5 variables. So this will allow me to mention something that we've used just to simplify the problem, which is invariant SDP, which is like just to use the most symmetry that you have. For example, in this configuration, there's an additional C2 symmetry that flips across this horizontal plane in yellow. And the statement of invariant SDP is that it's sufficient to impose the positive semi-definiteness of the matrix built out of those that transform in different irreducible representations of this symmetry group. So in this case, C2 only has 2, the even one and the odd one, so it's simple. So it's sufficient to impose this 6x6 matrix built out of these guys and the 2x2 of this guys. Okay, so just to mention that we're also using this. But okay, so how you do this in practice, of course, is just an example. Here is the spin configurations on this 1-3-1 diamond that lie to the right of the reflection plane. We have the empty one here, the guy with 2 adjacent sides, the one like this, and the even ones like this, and so on. On this side, we have the reflected guys across the plane, so on the left-hand side of the same guys. Now what you do is you multiply them together and evaluate the correlation function. So for example, this guy times the empty one is just the one that we gave a name here, x1. And then this one times this one, for example, the middle guy is repeated. So it's squared, so it just gets killed. So it's this x2, whereas the correlation function with a space in between. Okay, just to show that this is very explicit. And of course, imposing this positivity condition, reflection positivity, combined with the first ingredient that I talked about, the relation between these variables in blue, that recall that these in blue are some linear function of the other ones. Then imposing these two combined, at least the ways these two combined, then they'll imply some non-trivial bounds if we phrase it as an SDP. Okay, so that's basic strategy. But let me here mention also 2 other positivity constraints, which I also won't have the time to discuss the proof, but if you wish to learn more about these are nicely described in a textbook by mathematical physicists Gleim and Jaffe. So these are slightly more sophisticated kinds of positivity constraints. But they look simple nonetheless. So it's just that every spin correlator is positive. In this one, the second Griffiths inequality, it says that to take the product and then evaluate the correlation function is going to be bigger than if you do them separately. Okay, so I'm mentioning this because some of these are even non-convex, and we haven't found a way to efficiently make use of these. But we
should complement things.
Yeah, so that's what we're exploring right now, and I should say that we're relatively newbies at this whole business. So that's us.
Because typically you write those as a convex inequality in just one dimension bigger. Right?
One dimension bigger.
Well, we can write it later.
Okay, we can discuss this later. I would be happy to learn how to impose this in an efficient way. Okay, but we'll mostly focus on this because that's the easiest thing we can do, and we'll see that it leads to strong results. So just a few facts. Okay, these are only true for the ferromagnetic case, so again, focusing on this. This one in particular implies that all the correlation functions are monotonic functions of the coupling J or the magnetic field H. So that's an important consequence, and we'll come back to that. And this is just what I just mentioned. Some of these are non-convex, so we don't have an easy way to impose them.
This is the thing that you didn't deal with using the relaxation.
Yeah. So we tried some very naive ones, just totally naive, not like a systematic way, and it didn't improve too much. But we'll hope to learn how to do that in a systematic way.
So the first one, A has to be even, or what happens with S goes to minus S?
Right. So that's a good point. So that's the whole point, right? In the symmetry breaking phase, they can be non-zero. That's the non-trivial part. But they still have to be positive. Yeah, they have to be non-negative, but they can be non-zero, right?
No, these are under the assumption H is non-negative.
Yeah.
Oh,
right.
Sorry. Yes. That was your question. Yes.
Definite sign magnetic field.
Yeah. If you want, we're looking at the phase diagram in the first
There
quadrant.
is the other state where H is negative and S is negative.
Yeah, but the symmetry they're related. For the minus, the magnetic field with the minus sign is going to be just minus of that value. True. So that symmetry is still there. Okay. So this slide is just going to phrase it on SDP. So bear with me. There's a bunch of equations here, but the important problem, just the basic procedure is like, okay, we write down all this positive semi-definite matrices as we saw in the previous slide. Plug in the solution to the spin flip equations, just linear equations like this. So these are just like plug this into that. And then you're trying to solve this SDP problem. Minimize one of the variables, some cost function, in the function of the independent variables, linear function. Subject to the first Griffith inequality, the easy one. It's just that it has to be positive. And subject to the reflection positivity constraints in terms of these positive semi-definite matrices in terms of the independent variables here. And K is just labeled for each E-rep using SDP. Okay, so let me just mention here that we solved most of this SDPs using MOSEC, but mostly for the most precise results, we had to use SDPA because it was just because we needed more precision that somehow was not enough with MOSEC to deal with. And I'll tell you about this. So again, this is for the optimizers experts, just to get an idea of how big this problem is. So for instance, in the largest region in 2D, there was 29 independent variables that we saw, and 8 semi-definite positive matrices of these sizes, 288 and 200-ish were the largest one, so it doesn't look too bad. So it's relatively small. And for 3D, it was a little bigger. There was like 600-ish independent variables. A few more positive semi-definite matrices. For example, the largest one was 2400. And this turned out to be a little too big in our experience for the SDP solvers, even as it was just too slow. So one thing we did is just to truncate to the first 100 by 100, just something totally naive. So we dropped a bunch of information, but still imposed some positivity, and it still led to some results, some rigorous results. Let me also mention here that the problem seems to be that there was some large scale separation in the entries of these matrices. Somehow the smallest and the largest entry were on the order of 10 to the 10. So effectively, we lost 10 digits of accuracy. So if we really wanted to get precise result, we had to use like this SDPA quadruple double that had more digits of precision. And when we didn't need that, we can use MOSEC, which is a much faster one. But yeah, so this I'm showing so in case somebody has some words of advice of how to tackle such problems. But okay, so let me just in the last minutes come to the results. Okay, so first the 2D and the at zero magnetic field. So the blue is not so good. Okay, so the gray dots here are not so strong bounds, but are just from this tiny region. Okay, and the blue ones are for this slightly larger region. And as I told you before, the 2D is zero magnetic field is actually solved. So this would be a test just to see how good it is. And so the exact result is plotted here in black. So we see that even just going from a tiny region to a slightly less tiny region, it does get improved quite dramatically like this. The bound, the upper and lower bound get really squeezed into the analytical result. Yep.
This is not the same curve that you had before.
No, sorry. Yes, I forgot to mention. I'm plotting the correlation function of the pair of the two adjacent ones. Yeah, I'll come. The next slide is about the single one. Okay, so the next one looks like this. So this is again the plot that I showed before, the single spin correlator, which is the diagnosis for the phase transition, which occurs here. So as we can see, we have the results for the small diamond, like here. And here we see already kind of the role that the first Griffith inequality is playing. So for the most part, it's actually the same with the ticks here. But at some point, it actually drops to 0. So it does know quite a bit of, it does rule out all this region. So it does know something. But maybe I shouldn't oversell that too much, because once you go to a larger region, in this one, without imposing the first Griffith inequality, it's already doing better than this guy. And of course, if you include it further, then you get a tiny improvement, like this. Okay, and by the way, here I'm just plotting the upper bound, because the lower bound is just 0. Okay, so that's the rule of first Griffith inequality. Maybe perhaps not so important.
Right, is that true for J above JC as well?
Yeah. So it's always here for this particular one, for the single spin correlation.
Oh, okay.
Yeah.
So, are you inputting a non-zero value of the magnetic field to derive this amount, or what is the value of the magnetic field?
You're supposed to think about this curve as the limit as the magnetic field goes to 0. So that's the correct procedure to think about this. It's a tiny one, and you take the limit.
The bound itself is derived at h=0 for this particular.
Oh yes. Sorry. That's what you were asking?
Yeah.
So it's precisely at h=0.
So how do you break the symmetry between positive and negative magnetic field in this case? Why is?
Oh, so it's just that the positivities allow for this symmetry breaking. So one way to think about it, if you want, is that before taking the infinite lattice limit, you can take boundary conditions and say the boundary conditions are pointing up, and then you let fluctuate everything in between. Then you take the limit as the lattice system goes to infinity. That's still allowed by all the positivity conditions that we imposed. So, and similar for down one, for example. But here we're restricting to the positive one. So it should be allowed by the positivity constraints. And we do see that we do observe this. Okay, so that's spontaneous magnetization. And let me show you this plot. So what I showed you here was the h=0, for example, so going along this line. Now, I'm going to show you the ones with non-zero magnetic field, which is not solved analytically. So these you can view these as new results. And here I'm showing both the upper and lower bound, but you can see it's mostly non-noticeable, except for here that we just saw in the previous slide. And so it's probably better to look at this plot, which is just a difference between the upper and lower bound. And you see that there's some regions here for some largest magnetic field that the error is quite tiny. It's 10 to the negative 15. So it really pins down the actual value of in this case the two adjacent correlator. So it depends on what you mean by solving it, but if you have the answer to 10 to the negative 15, you can say that it's solved in some sense. Okay, and the error does get a little bigger in this region. Of course, the biggest error is around precisely the critical point in these plots. Okay, since I'm running a little short on time, I'll skip this analysis. We're comparing to Monte Carlo, and it's nice to see that in some regions we're much better than Monte Carlo studies. But of course, the advantage on top of Monte Carlo is that these bounds are rigorous as opposed to Monte Carlo, whose error bars are of statistical nature. But I'll have to skip this. Here are more examples of bounds. As you can see, some for largest H for the two-spin correlator, the single-spin correlator. You can't really see the difference in the upper and lower bounds, so this is basically what the function looks like. It's just squeezed into the actual result. And the one thing that I wanted to point out is maybe not the tightest bound, but for example, this one is a little hard to see, but the gray ones here, they feature something that is not monotonic. And as we saw, one consequence of the second Griffiths inequality is that the spin correlators have to be monotonic. So somehow we didn't impose the second Griffiths inequality, but the expectation is that if we did impose it, then the bounds should have to tighten up into something monotonic. So let me say that here. For example, here's an example of these. So I'm just focusing in on, for example, this guy in this gray region, which look non-monotonic. You can explicitly check that the bounds in this red ones, the red color means that some Griffiths inequality is being violated. So I'm just saying that if we somehow manage to impose second Griffiths inequality as well with some relaxation of something, we do expect the bounds to keep improving in this way. Okay, let me finish. So this is about the second Griffiths inequality. Let me skip this in the interest of time.
You're saying that doesn't matter?
So for example, this one it's not a relaxation. This is just because we can write this one. So there's some special ones that are related by symmetry when this B is related by symmetry. So this actually just becomes a square. And that we could just phrase exactly like this. So there's no relaxation. But it just turns out that those don't improve the bounds. The ones that are of more general form like this, where it's not the square of something, that we do need to relax in some way, those are the ones that are explicitly violated. There's some examples here. So those are the ones that we didn't impose, we didn't try too hard, but we didn't find a good way to relax, and those are the ones that we expect to improve the bounds.
So in the first one, A and D are completely unrelated?
Yeah. And then there's many, as you can see. It could be anything you want. There's plenty. So we do hope to, in the future, try to tackle these as well. Okay. And lastly, I just want to show you the 3D results, which are not as tight, but encouraging nonetheless. Here is just for increasing size of the diamond that we consider, like this, in gray, and then in brown, and then in blue. But again, the blue, we had to drop some positivity condition. We had to truncate the matrices to 100 by 100 just because it was too slow. And so these are the results for the two adjacent spin correlators. Okay, so let me finish here. I just flashed the slides, but since I'm out of time, let me pause here and thank you for your attention.
Any further questions for Victor?
Yep.
I see that some of it is already on the transparency, but there are inequalities which have been used for rigorous results about the critical behavior. More so than Griffith's inequality, which is shown. In particular, Simon inequality says that if you're at the critical point, then the sum of the two-point function from 0 to the boundary of an arbitrary box has to be greater or equal than 1.
Right.
Does this, and that is, in a way, the fact that it's close to 1 is another signature of being critical. Has this type of inequalities be useful?
Well, that's what we're currently trying to incorporate, and this was in fact one of my comments, that this time we leave inequalities. We hope to, it's similar to the second Griffiths one, and as far as we just in a practical way to square something. And yeah, they are very deep results that we hope to incorporate to the naive one that we used. Hopefully, it can increase, for example, corporate information about spin correlators that are a little further away, as you mentioned. But we haven't found a way yet, but also we just started thinking about it. So we hope to be able to report on this soon. But yeah, so there's many inequalities that you know very well that are very strong, and we hope to indeed try to incorporate those.
I mean, it's clear that just by plugging in the bounds we already have for the short distance correlator, that can make a prediction about the mass gap or bound to the mass gap when you're sufficiently away from the critical point. But what we want to do is to feed this inequality directly into the SDP. That we haven't been able to do yet, but trying to do that.
Yeah.
So the matrices that you produce that you want to impose positive semi-definiteness, are they just filled with variables in some combinatorial way, or do you have some complicated linear functions?
Yeah, so it's just, it's some variables at first, and then you plug in the solution to spin flip equations, but it's still linear. So it's, so some collection of matrices that depend linearly on some variables.
I see, but in the end, you will not have kind of not a simple structure where you just have variables. You will really have linear.
It's not a linear problem. Yeah.
So he's asking if each entry is just a variable or a linear combination of different variables.
Oh yeah, it's the second one. Yeah.
Can you say something about the partition function, or is it just, so this gives you bounds on the correlators, but if you want something about the partition function, the log partition function, the free energy?
Oh, right. Well, we haven't studied that, but I guess in previous talks I learned that you can try to, your cost function can be some something else, and maybe we can put bounds on that, but I can't say much more than that.
Actually, I think if you think of free energy, for example, these spin correlators give rise to exactly that, because free energies are derivatives with respect to the temperature. So
right, I see.
Indeed encode information about the free energy.
Sure.
So I think maybe one equivalent way to put that is that I think the spin correlators look like moments of the distribution.
That's right.
So you can put, to truncate moment conditions and try to get bar for the zeroth moment, which is the partition function.
That's right.
Yeah, thank you. Yep.
So that's another comment. It's a bit strange from a certain perspective. How does the dimension dependence enter here? It seems that from what you described, the higher dimension, the more complicated the diamond and more variables.
Yeah.
And yet the critical behavior simplifies in high dimensions.
That is true. Yeah.
Is there a way to leap over the intermediate trouble and get the message about long distance?
That would be
quantities?
That would be one hope, because as you say. So for example, one thing is that even the bounds that we get are weaker around criticality. So somehow we want to follow a different approach if we really want to zoom into the critical behavior.
Yeah.
And then
find a way to identify relevant variables.
Exactly.
Long distance behavior.
Exactly. And I have one comment here about null states, and just in a talk yesterday by Pablo, we had some idea of, mentioned some possible way of try to use this structure, this big matrices have some null states, and there's way to harness that information and to try to identify these, just focus on these null states and try to improve the algorithm this way. So maybe hopefully might lead to something like what you're thinking of. And another way that it's totally open is like maybe you can combine this somehow with the conformal bootstrap, which is focused at the critical point. But that is open waters. But that's also an interesting thing to think about. Yep.
I guess the reason that you got in the constraint equations a finite number of terms was because here the variables take value in Z2. right? So if, for example, you have continuous degrees of freedom, can you still do that, or this approach?
Well, you still get an equation, of course, but yeah, it won't be finite, right? Yeah. So, but you can get different kinds of relations. For example, we'll hear about it in maybe in the next few talks of things about dynamical systems, in which the relation between them comes from the equation of motion itself, the differential equation. And those have to be satisfying correlation functions. So that's a different, that's a continuous version of that, but also a useful relation between them, and it's finite and so on. So I believe that we'll hear about it in a different talk.
The equation will be finite if the interaction is polynomial. So for phi 4 theory, we can also do it. But the number of variables will be much bigger because you have arbitrary power of the field at every site. So it's much harder to do this for phi 4 theory on the lattice. With the same approach.
When you expand the difference in the energy, wouldn't you get just infinitely number terms, and then you don't know how to truncate it?
You expand what, sir?
In your approach, you also expand the difference in the energy because of this change of variables, right?
Yeah.
So you'll just get infinitely many terms, right?
No. The equation derived by saying that total derivative with back to the field in the path integral is equal to 0, right? So if you act that on the e to the say interaction potential, you just put down finite powers. So again, the equation involving only finite many field insertions.
So it's a different type of relation. It's like the equation of motion that you use.
Okay, it's a different one, not this one.
I think so.
The one that you did by changing variables.
Yeah. I mean, it could be phrased like that, right?
I see. Okay. I think I see your point. Okay.
It's the same. It's like a word identity.
Yeah. Okay. Makes sense. Okay. Yeah. Okay.
But yeah. But the problem is different, that you have infinitely many variables, as she said.
Yeah. Just infinitesimal you can do. Yeah. Okay. Makes sense.
Yeah.
You've had many relations and few independent variables. Mm-hmm. Is there a simple way to count how many independent variables there are? Or how many relations you expect? Or did you just write them all down and then figure out which relations are independent?
So that's what we do in practice, but I don't have a good estimate of how to a priori guess how much it will be cut down. Yeah.
All right. If there are no further questions, let's